So we're going to continue on with some more comparison tests. Remember, the goal here is just to determine whether a series converges or diverges. If it converges, we probably won't be able to figure out what it converges to. The most we can do is say, does it converge, or does it eventually approach a number, or does it diverge? The first test we're going to look at, and these are just two tests, they are our comparison test. So the first test is called the comparison test. And what it says is, let's say you have these two series, A sub k, B sub k. Let's look at the first criteria. Let's say that the A sub k is smaller than or equal to the B sub k. And let's say that we know that the B sub k converges, so the larger one converges. What we can conclude from this is that the A sub k also converges. So off to the side, I'm going to kind of show you what this means. So this is just a sad sketch. So remember, this said if B sub k converges, then A sub k converges. Converges mean it's going to approach a sum. So if we were to look at the graph of a series that converges, it would be something like this, right? It's approaching the x-axis fast enough so that we can get a sum. So let's say this is our B sub k. Now remember, our A sub k is going to be less than or equal to, and since our B sub k approaches the x-axis, it's going to kind of force the smaller one, A sub k, to also approach the x-axis fast enough to converge. So if the larger converges, the smaller converges. Let's go back to our comparison test and look at the second criteria. So let's look at number 2. Let's say that the series B sub k is smaller than or equal to A sub k. And let's say that we know that B sub k diverges. Then if the smaller B sub k diverges, then the larger A sub k diverges. Going back to a sad sketch. So remember, our B sub k was smaller and it diverged. So when you talk about a divergent series, that typically means that it's getting larger and larger and larger and larger. So the sum is always getting larger, larger, and larger and larger. So if this is our B sub k and it diverges, and our A sub k is larger than or equal to, so it's going to be above, notice that the A sub k is getting larger as well. So larger diverges, or smaller diverges, then larger diverges. The challenge of using our comparison test is we have a series. So if we look at example 1, we have a series. Our A sub k is equal to 6 to the k over 5 to the k minus 2. So I have an A sub k. I need to find a B sub k. And the series that you're going to compare it to, your B sub k that you have to find, just depends on your A sub k. So you want to pick something similar, but you want to pick your series so that you can easily determine whether it diverges or whether it converges. When I look at my A sub k, I notice that k is the exponent. And when k is the exponent, I think of a geometric series. If I ignore that minus 2, remember I want to pick something similar that I can determine convergence or divergence. So if I look at B sub k being 6 to the k over 5 to the k, and I ignore that minus 2, then notice this is 6 over 5 to the k. So the series from k equal to 1 to infinity of this new series, 6 over 5 to the k, is geometric. So I found a similar series that I can easily determine whether it diverges or whether it converges. So notice here, r is 6 over 5, which is greater than or equal to 1. So this series diverges. So I found a series to compare my a sub k to. And I know this series b sub k diverges. So what I'm looking at is I'm looking at criteria 2. So now the only thing left to show is that b sub k is less than or equal to a sub k. So just because I found a series and I know that that series diverges, I'm not done. I have two things to do. I have to first find a series that is divergent or convergent. Second, I need to show if that series is smaller or larger than my given series. Well, how you do that just depends on the type of series you have. So let's just say that b sub k, which is 6 to the k over 5 to the k, this is what I need to show, that it's less than or equal to 6 to the k over 5 to the k minus 2. And there's a variety of ways I could do that. One thing I could do is I could multiply both sides by 5 to the k minus 2 and divide both sides by 6 to the k. You got to be careful though, because this is an inequality. So you want to make sure that you're not dividing or multiplying by a negative value, or else you have to flip the sign. But my k value starts at 1. So I know that these values will always be positive. What that gives me is 5 to the k minus 2 over 5 to the k less than or equal to 1. Is that true? Okay, remember that's what I'm trying to show. Well, this is 1 minus 2 over 5 to the k. Is this less than or equal to 1? Yes, because 2 over 5 to the k, that's always going to be smaller than 1. Okay. But it's also greater than 0. So 1 minus some small fraction that's less than 1, that's going to give me a value that is less than or equal to 1. Or another way to write this is 2 over 5 to the k is between 0 and 1. But remember, the k starts at 1, so for k greater than or equal to 1. So we have to make sure this is true for all our k values. So now I've just shown the inequality that I needed, and I found a comparison function that diverges. So this fits criteria number 2. B sub k is less than or equal to a sub k. B sub k diverges, so I can conclude that a sub k diverges. This is what I would write. Thus, so, therefore, whatever you want to write. So the series that I was given in the beginning, from k is equal to 1 to infinity, of 6 to the k over 5 to the k minus 2 diverges. That's my conclusion. But I have to justify it by the comparison test, or by comparison test. I'm going to leave out the. Okay, so again, find a similar series that you can easily determine whether it diverges or converges, and then show the inequality. Let's try another one. Example B, we're looking at the series natural log of k over k to the 4th. All right, so my a sub k is equal to the natural log of k over k to the 4th. And I got a problem here. I have no idea what to compare it to. Oftentimes when you have a series that is a fraction, you can kind of get a sense of whether it's going to converge or diverge. Natural log of k grows very, very slowly. Look at the graph. And in fact, you can put in natural log of x over x to the fourth in your calculator, and you can see that x to the fourth, the denominator here, grows a lot faster than the numerator, which is natural log. So it's a fraction. If the bottom is growing very, very fast, but the top is growing very, very slow, the fraction itself is getting closer and closer to 0. So it's probably going to converge. So now I have to look at the natural log of k and the k to the fourth, and I have to try to think of something to compare it to that probably converges. And it's the k to the fourth that I'm looking at, because that looks like a p series. Think of 1 over k to the fourth. That would converge. However, showing which one is smaller and which one is larger is going to be really difficult. So instead of actually starting out with choosing my b sub k, I'm going to just look at natural log of k. I know this is true. I know that the natural log of k is less than or equal to k for k values greater than or equal to 2, and I'm choosing 2 because that's where my series started from. So if I simply divide both sides of this inequality by k to the fourth, I know the natural log of k over k to the fourth is less than or equal to k over k to the fourth. This is going to be my b sub k. And if you reduce it, it's 1 over k to the third. So the series from k equal to, we started at 2 to infinity, my b sub k, it's 1 over k to the third. This is a convergent p series because here for this p series, I have p is equal to 3, so this converges. So I've already shown that my b sub k is greater than or equal to natural log of k over k to the fourth. And I know that b sub k converges because it's a convergent p series. I'm done. By the first criteria that I must have that my series that I was given, which is natural log of k over k to the fourth, it has to converge by the comparison test. The challenge here is finding an appropriate series. And now you didn't have to choose the one I chose. As long as you can determine whether the series that you're choosing converges or diverges, and you can show which is smaller and which is larger, then you can use any series you want for comparison. The difficulty here is often determining which one is the smaller and which is the larger. Which brings us to our second comparison test. The second comparison test is called the limit comparison test. Again, you're going to look at two series, an a sub k and a b sub k. But instead of showing which is the smaller and which is the larger, you're going to take the limit of the fraction a sub k over b sub k. And you're going to look at the three criterias given the limit. The first one, if the limit is some number between 0 and infinity, then both converge or diverge. Or, criteria 2, let's say the limit is 0. Then if the b sub k converges, then a sub k converges. So if the denominator converges, then the numerator is going to converge. Well, let's say that the limit is infinity. Well, then if the b sub k diverges, then the a sub k is going to diverge. So a little bit different. You still have to find a series to compare it, but you don't have to show which is smaller, which is larger. You just take the limit and you see if it falls under the 1, the 2, or the 3 criteria. Example 2, we want to determine if this series converges or diverges, and it's sine of pi over k. So think about sine. It's going to have a bunch of values, and here my k value starts at 2, so sine of pi over 2 is 1. When k is 3, sine of pi over 3, then you have pi over 4, and so on. So pi over k is getting closer and closer to 0, but that doesn't mean it's going to converge, right? Because we had series that were getting smaller and smaller and smaller, but the sum itself was not approaching a number. I want to find a series to compare my a sub k to. So again, a sub k is sine of pi over k. There's a little trick with trig functions. Often, all you have to do is look at the argument. And in this case, it's going to be pi over k. The reason why I chose pi over k is because I know that if I take the limit of these two, something nice will happen. Okay, so the only thing I need to do is determine whether my b sub k converges or diverges. So let's look at the series from k equal to 2 to infinity of my b sub k, which is pi over k. I can factor out the pi, and then I'm looking at this series from k equal to 2 to infinity of 1 over k, and that's a divergent p series where p is equal to 1 or harmonic. So this diverges. And the justification is p series where p is equal to 1, or you could use harmonic, means the same thing. So I know that the b sub k diverges. Now all I have to do is take the limit. Again, I don't have to show which is smaller and which is larger. So the limit as k goes to infinity of sine of pi over k over pi over k. Now as k goes to infinity, that's sine of 0, which is 0. And in the denominator, as k goes to infinity, I have pi over infinity, which is also 0. This is an indeterminate form. What I'm going to do is I'm going to simply take L'Hopital's, which means I'm going to take the derivative on the top. So the derivative of sine is cosine, chain rule, right? So it's cosine of pi over k times the derivative with respect to k of the argument, pi over k. And then when I take the derivative in the denominator, and here I'm not going to, I'm just going to write out that I'm going to be taking the derivative of pi over k. And that's another reason why I chose my b sub k to be the argument, because I actually don't even have to take the derivative. This is a fraction, these values are the same, they cancel. So if you choose the argument, all you have to do is know that the derivative of the inside is going to be the same as the derivative of the denominator, and they'll cancel. Now, this is going to be equal to cosine of, as k goes to infinity, it's cosine of 0, which is 1. So I took the limit, and the limit was 1, which is criteria 1. It's between 0 and infinity. So since I know that b sub k diverges, then I know a sub k diverges. Your conclusion would be that the series from k equal to 2 to infinity of sine of pi over k diverges by limit comparison test. All right, so you see the advantage of doing the limit comparison test is you don't have to show which is smaller, which is larger. Our last example, again, this is a really short section. We have this series. Notice that my a sub k is a rational expression. In my head, I'm thinking, oh, okay, well, The degree in the denominator is larger than the degree in the numerator. So this is getting closer and closer to 0 since the bottom is growing faster than the top. I'm thinking it probably converges. I have to pick some similar series to compare it to. Now there's an easy way to pick your series when you're dealing with rational expressions. Just use the largest term, which in the numerator would be the k. So pick the largest term in the numerator and denominator. And the denominator would be the 2k to the third. Choose that for your comparison series, because then it will simplify. In this case, it's going to be 1 over 2 times k squared. So notice that if I look at the series, my comparison series from k equal to 2 to infinity of 1 over 2 times k squared, I can factor out the 1/2, and I get 1 over k squared, which is a convergent p-series. Since p is equal to 2. So I know that my b sub k converges. Now all I have to do is take the limit. We're going to take the limit as k goes to infinity of, a lot of writing here, k plus 5 over 2k to the third plus k minus 3 all over 1 over, actually I'm going to keep the 2 underneath there, right? 2k squared, because my b sub k was 1 over 2k squared. So that's kind of a mess to evaluate. I'm going to clean this up by using properties of fractions and have times the reciprocal of the denominator. So I'm going to multiply this by 2k squared over 1. Okay, now multiplying through, I get this limit of 2k to the third plus 10k squared over 2k to the third minus k minus 3. So at this point, when you take the limit, it's going to be infinity over infinity. And you have a choice. You could use L'Hopital's, or I'm just going to, because I don't want to use L'Hopital's, it takes too long. I'm going to go ahead and divide everything by k to the third. That'll give me 2 plus 10 over k over 2 minus 1 over k squared minus 3 over k to the third. And now as k goes to infinity, the 10 over k goes to 0, 1 over k squared goes to 0, 3 over k to the third goes to 0. So this limit is simply 2 over 2, or 1. And then we have that our series will converge by the limit comparison test. So that's therefore whatever. So this series, k plus 5 over 2k to the third plus k minus 3 converges by limit comparison test. And that's it for this section, just these two comparison tests. In one, you have to determine which is the smaller, which is the larger. In the other, you just have to take the limit. In both, you have to find a series to compare it to. It's going to be a similar series where you can easily determine whether that series converges or diverges. And that's it.